Today, we're going to follow a single chemical sample on a pretty incredible journey. We're going to see how scientists use immense pressure to sort molecules, and in the process, we'll get to know a true cornerstone of modern chemistry, high-performance liquid chromatography.
So just imagine you've got this complex mixture. Maybe it's a blood sample, a little bit of river water, or even a brand new drug that's being developed. How on earth do you isolate and measure every single little thing in there, especially that one specific molecule you're looking for? Well, that is the exact problem HPLC was invented to solve. At its heart, chromatography is really all about separation. You can think of it like a chemical sorting machine. But HPLC, oh, it's not just any sorter. It is a supercharged, high-pressure version that cranks up the precision and the speed to a whole new level.
So what's the official name? High-performance liquid chromatography, or HPLC. And the one thing that puts the high performance in the name is actually simple but totally revolutionary. Powerful pumps. See, instead of just letting a liquid drip through a column with gravity, HPLC uses massive pressure to force it through. When this tech showed up back in the 70s, it was a complete game changer.
Okay, before our sample starts its journey, we need to set some rules of the road. In HPLC, the separation all comes down to how different molecules interact with two key things: a liquid that's moving through the system, we call that the mobile phase, and a solid material that's packed inside a tube, which we call the stationary phase.
Now, there are two main rule books for how this separation can happen. In what we call normal phase, the solid material is polar. You can think of it as water-loving. This means that polar molecules in your sample are going to stick to it longer, while the nonpolar molecules just rush right on by. But reverse phase, which is way more common these days, it just flips the script. The solid material is nonpolar, so it grabs onto other nonpolar molecules, letting all the polar ones leave first. It's all just a simple game of chemical attraction, really.
All right, with the rules all set, our sample is ready to go. So let's follow it, step by step, through the main parts of an HPLC system.
First stop, the pump. This is the absolute powerhouse of the entire operation. It takes the mobile phase, our liquid solvent, from its container and gets it moving under some serious pressure. You really can think of it as the engine that drives this whole machine.
And, we're not talking about a gentle push here. We are talking about pressures up to 6,000 pounds per square inch. That is an incredible amount of force, and it's what lets us push the liquid through a very, very tightly packed column. And that's the key to getting a fast, efficient, and super reproducible separation. This pressure right here, that's the high-performance part of the name.
So, we've got our high-pressure liquid flowing. Now it's time to introduce our sample into the mix. The next stop is the injector. This is the starting gate for our sample's big race.
The real genius of the injector is just how simple and precise it is. It uses a special two-position valve. So in the load position, you fill up a tiny loop with a very precise amount of your sample. Then you just flick the switch to inject. The valve instantly reroutes that high-pressure liquid from the pump, and it pushes your entire sample out of the loop and into the system as one single tidy little plug.
And now for the main event. The sample gets swept from the injector and goes directly into the column. This right here is the true heart of the HPLC system. It's the racetrack where all the separation actually happens.
Now, there are actually two columns our sample is going to meet. First, it hits the guard column. This thing is like a bodyguard, It sacrifices itself to catch any junk or impurities that could clog up or ruin the much more expensive main column. Then it enters the analytical column. This is a stainless steel tube packed with that stationary phase material, and it's here over the length of this column that all the different molecules in our sample separate out, moving at different speeds based on those rules we set up earlier.
So the separation has happened, but all the molecules are still totally invisible to us, just dissolved in that liquid. So how in the world do we actually see the results? Well, that's where the detector comes in. As these separated little bands of molecules exit the column, they flow directly into our final component, the detector. This is the finish line, where each and every molecule gets spotted as it crosses. And picking the right detector is absolutely crucial. The most common one is a UV-Vis detector, which is great for pretty much any molecule that absorbs light. But what if your molecule doesn't? Or what if it's fluorescent? Well, then you'd want a fluorescence detector for way more sensitivity.
Other types can measure tiny electrical currents or even how light bends as the sample flows by. The detector is really the specialized tool that makes your specific molecule of interest pop out and become visible.
So the final result of all this is a graph, and we call it a chromatogram. Each one of those peaks you see represents a different component from your original mixture. The time it took for a peak to show up, that helps you identify what the molecule is, and the size of that peak, the area underneath it, tells you exactly how much of it there is. And just like that, the invisible becomes visible, and more importantly, quantifiable. Okay, so we've seen the whole journey, but why does all this incredible technology really matter? Let's zoom out for a second and see how HPLC is used to solve some major real-world problems.
Because, of course, you can't just stick a rock or a leaf directly into a multi-million-dollar machine, right? Real-world samples need some careful prep work. Solids might need to be dissolved, and liquids often need to be cleaned up or diluted. This whole prep step might not be the most glamorous part, but it is absolutely critical for getting clean, reliable results, and of course, for protecting the instrument itself.
So why is HPLC such a powerhouse in the lab? Well, for one, it's incredibly precise and sensitive. It can also be automated to run hundreds of samples a day without a break. But I think its real superpower is its versatility. It is the go-to method for any compound that you can't easily turn into a gas, which covers a huge range of important molecules, from pharmaceuticals to pesticides to pollutants. That versatility makes it a completely indispensable tool in just about every scientific field you can think of. From making sure a life-saving drug is pure, to detecting tiny traces of pollutants in our water, to finding the markers for a disease, HPLC gives us the answers. It really makes you wonder, doesn't it? What critical information is just waiting to be separated and discovered in the very next sample that gets injected?